we're going to be looking at a lot of related rates examples in this section. But in this first example, I want to really slow down and take my time and illustrate the problem-solving process of solving these related rates problems, because there are a lot of steps and they do tend to be difficult and intimidating when we're first starting off. So we're going to look at this first example, which says a 26-foot ladder is placed against a wall. If the top of the ladder is sliding down the wall at 2 feet per second, at what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet away from the wall? So in this first example, this first step, I may not always do this step because it's not always helpful, but this is a really good example where it is helpful. I'm going to draw a picture. In a lot of these geometry-based problems, I think drawing a picture can be really, really helpful in visualizing what's happening within our problem. So we have a wall, and then maybe here is our ladder, and then everything is resting on the ground. And if you want to draw in your ladder to make it easier to identify or just to show off your wonderful art skills, please feel free to do that. So this is what our picture sort of looks like here. And hopefully when we draw our picture, we should see a shape that we can identify. Here's my wall, here's my ladder, here's the ground. I look at that and I see a triangle, and not just any kind of triangle. I see a right triangle. So this, first of all, is going to be really, really helpful to us in just a little bit, that we have this right triangle. So we've got our picture. It's kind of a really nice start, and I'm going to use this picture to really help me organize all of the information in this problem. So in step 2 here, step 2, I want to identify all variables, all of the variables that I'm going to be using. I want to give those variable names, and I want to identify the values of those if I know them. So I look at this again. Over here we drew a right triangle. When I see a right triangle, I think about a squared plus b squared equals c squared, our Pythagorean theorem. So I'm going to call this side A. I'm going to call this side B. A and B, those sides, it doesn't matter which side is which, but remember C should be directly across from the right angle. It's the hypotenuse. It's also the longest side of our right triangle. So this side is going to be C. So I'm just using these A, B, and C as variables for the lengths of each of these pieces of my triangle. These are going to be what we're using throughout this problem. And now, if we can, I also want to look at our problem and identify what pieces of information were given to us. So if I go back and read my problem here, it's first of all says a 26-foot ladder. So I'm just going to stop right there. The ladder, so this side of my right triangle, is 26 feet long. So that means that C is equal to 26 feet. I'm going to try and write all of the values of these variables and include them in my sketch. So we've got our 26-foot ladder. What else do we know? We know the top of the ladder is sliding down the wall at 2 feet per second. Now that's actually a rate, feet per second. It's describing a rate of change. We're actually going to come back to that in just a minute. We want to know at what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet away from the wall. So I know that the bottom of the ladder, the distance between the bottom of the ladder and the wall, is 10 feet. So that means B must be 10. Now this problem didn't give me any indication as to what A is, but we can use what we know, and in this case we know we're working with a right triangle. We know we're working with the Pythagorean theorem. So I'm going to go ahead and just solve for A really quickly with the Pythagorean theorem. So I know I'm working with A squared plus B squared. B is 10 squared is equal to c squared. That's 26 squared. So this is a squared plus 100 is equal to, oh, I don't know 26 squared off the top of my head. Let me grab my calculator here. 676. So if I subtract 100 from each side, that means that a squared must be 576. And if I take the square root of that, I believe, yes, 24. A is 24 feet. So that means that the missing side that I didn't have, A is 24 feet high. So here we have the missing piece of our right triangle, which we will need later on. So at this point, I've kind of identified all of the variables, all of the pieces of my picture. Sometimes you may be given an equation, in which case it might be helpful to identify, what values each of the variables in your equation are taking at a particular moment in time. But that's all I can really do with this first step. I've identified all of my variables. So step 3, this is going to be kind of a new step here. I want to express all rates as derivatives. So I want to talk about how each part of this triangle is changing over time. What's going on in this scenario? And sometimes I'm going to even add in little arrows to help me think about what's going on here. So first of all, it says the top of the ladder is sliding down the wall. So what's going to happen here? The top of the ladder is sliding down the wall. It's going down. The ladder itself is not actually changing distance, or it's not changing. It's always going to be 26 feet long. So we're going to come back to that idea in just a minute. So if the top slides down, the ladder itself stays the same length. That means that this piece, the bottom of my ladder, is going to slide away from the wall. I like to draw in these little arrows to help indicate what's changing in this picture, because it's going to help when we talk about the signs of our derivatives here in just a minute. Now, as we'll see in an upcoming step, we want to talk about how each of these sides is changing with respect to time. So I like to use the notation dA, the derivative of A, with respect to time. So dA over dt. If you want to use A prime there, you can. I think it's just a little bit less clear, but I'm going to use dA over dt. We'll also want to talk about either B prime or dB over dt. And then the rate of change of the hypotenuse, which would be C prime or dC over dt. Again, you can use either notation. I'm going to be using dC over dt for the most part in these problems, but for this first example, I'll try and use both. So I want to look for any rates that the problem gave me here. Let me erase some of the things I've underlined and highlighted to kind of clean up this part. So the only rate that I see in this problem, it says if the top of the ladder is sliding down the wall at 2 feet per second. Anytime we see per, right, feet per second, miles per hour, dollars per hour, something like that, that is going to be a rate, which I want to express as a derivative. So it says the top of the ladder, so that's this part right here, is sliding down the wall. That's the arrow pointing down that we drew. So it's sliding down the wall at 2 feet per second. So most of us would probably say, okay, well, the derivative, dA over dt, that should probably be 2. And you're almost right. There is one tricky part about this problem, though, and that's that the top of the ladder is sliding down the wall. If we think about how this side of my triangle is changing, I always like to ask the question, is this side getting longer or is this side getting shorter? Well, if the top of the ladder is sliding down, if it's going down, that means that this side of my triangle is getting shorter, which means that the rate of change isn't positive, it's got to be negative. So a prime, or dA over dt, that's actually going to be -2. So we've got -2 for our derivative of that side. Let's go back and read the problem and see what else is there. It says, at what rate is the bottom of the ladder moving away from the wall? So I'm looking for the rate of change of this side right here, of the bottom part of my right triangle. So that means I'm not going to know what dB over dt is. I'm going to put a question mark there because that's going to be what I'm solving for. And then it goes on, when the bottom of the ladder is 10 feet away from the wall, we've already used that information. So the one piece that we're missing is this piece right here. What's the derivative of c? And then after that, we'll be able to move on to our fourth step. Well, we said top of the ladder slides down. Right side, this is going to slide out. I want to think about, how is this side of my right triangle changing? How is the length of the ladder changing? Is it getting longer or is it getting shorter? Now, I said earlier it's actually not changing. It's not getting longer, it's not getting shorter, which means it can't be a positive number because then we'd be saying that the ladder is getting longer. It's not getting shorter, so it can't be a negative number. If it's not changing, another way that I can say its rate of change is 0. It's not changing. So we can say dc over dt is equal to 0. So here I've got this really nice picture, and I've got all of the relevant information that this problem has given me included in this picture. It's going to make the second half of our problem, the next video, a whole lot easier. It's going to make it much, much easier for us to work with. Before we wrap this video up, though, I want to talk about my fourth step here, and I want to find an equation that relates my variables. And we want something that works with all of the variables that we're using. So we're using A, we're using B, we're using C. Now, generally, well, I should say sometimes that equation will actually just be given to you. You don't need to come up with that every single time. But this is a case where we weren't given it. We want something that relates A and B and C. Well, don't think too hard because we've actually used an equation that relates A and B and C. We use the Pythagorean theorem. But instead of plugging in 10 or 26, I want to just leave those as variables. So I know one variable that relates A and B and C would be A squared plus B squared is equal to C squared. So this is going to be the equation that I work with going forward. I do think that these 4 steps, actually the first part of this problem, is the most difficult. It's kind of trying to comprehend all of the information that the problem gives you. But if you can organize it in this really nice way, in this nice way that we have in our picture right here, it's going to make the rest of our problem much, much easier. So that's something I'm really going to stress throughout the rest of these examples that we see today. I'm going to really try to emphasize how important information organization is in this section, because if you can write it down and make it easy to find and easy to identify, that means that the actual computation part of the problem is going to be much, much easier. So in the next video, we're going to finish this problem up. We're going to see the derivative taking process. So we're actually going to find the derivative of this equation with respect to t, and then we're going to solve for our missing rate, which we said again earlier was b prime or dB over dt.